So let me remind you just one more time our definition for average velocity. Average velocity is equal to distance traveled divided by the time spent making that change in position. However, we're sometimes interested not so much in an average velocity for some broad distance traveled. So, for example, when a pickup truck drives down the highway, there's no guarantee that it maintains a steady speed for the whole trip. But regardless, if I figure out the total overall distance traveled, that's delta x, and if I divide that by the time it takes to make the whole journey from initial to final position, that's the value of t, and I can get the car's average speed. But that's no guarantee that the number I calculate would be the exact speed the truck had when it was right here, unless it maintained a constant velocity. When something maintains constant velocity, its average speed and instantaneous speed are one and the same. The instantaneous speed at this point can be found by limiting myself. Instead of taking this whole broad overall displacement, what if I just narrowed down to, I compare its position at this moment in time and its position in this moment of time, then my delta x is getting smaller. And not only is my delta x getting smaller, but the value of time is getting smaller as well. So the little bit of time it took to go from this point to this point is getting closer and closer to zero. And in fact, if I zoom in and compare like just from that point in time until that point in time, then if my delta t becomes so small, so close to zero, that it's like the smallest interval I could possibly measure, I change my notation. Instead of calling it delta t, I call it dt. And instead of calling it delta x, I call it dx. So the definition is still basically the same. If I want instantaneous velocity, I'm going to divide an interval, right, a distance traveled, by the time it takes to make that change. But as long as I limit myself to cases where that time interval is approaching zero, then the notation changes, and we just call it dx divided by dt. So it's a very small distance divided by the corresponding small interval of time. All right, that's all repetition from a previous lecture. Well, in the same way, now we want to define not velocity, but acceleration. So if you watch much sports, you might hear the broadcasters make this statement about an athlete. Sometimes you hear something like, hey, she's really quick, even though she's not really fast, right? I guess the implication there is if you have an athlete who isn't able to achieve a really high top speed, but she can get from the low speed to the high speed in a very short amount of time, we say they're quick if they can make sudden changes in their speed, even if they're not fast, even if they're not able to achieve a very high overall speed. So this hints at the idea of acceleration. If speed is the rate at which we change our position, so whenever we use the phrase rate, we're sort of implying we're going to divide something by time. So think of like rate of pay. So yeah, if you earn an hourly wage, then your rate of pay is some number of dollars per hour. Or if you're curious, what's the rate at which water flows out of your shower head? Okay, that's not just the number of gallons is not the rate. It's the GPM. It's the number of gallons per minute. So as long as we're expressing a quantity divided by time, then we're often referring to some rate. So velocity can be thought of the rate of change, right? We use the symbol delta. So delta x, change in position. So velocity is rate of change of position. So in the same way, acceleration is a rate, and it's also a rate of change. But it's not the rate of change of position, it's the rate of change of velocity. So just like average velocity is delta x over t, average acceleration is delta v over t. And if I want instantaneous acceleration, then I limit myself to cases where delta t approaches 0. And in that case, the symbols change. We call it dv dt. Okay, so if we limit ourselves to examples of uniform acceleration, then there's no difference between the average value and the instantaneous value. Uniform means the value is always the same constant value, just like it is with free fall. Acceleration due to gravity is always 9.8 meters per second. So if you climb to the top of a tall tower, you stand at the edge of a cliff, and you lean out over the edge of the cliff and you drop a rock, and it falls and falls and falls. Something certainly is increasing as it leaves your hand and approaches the water down below and splashes in. The position is increasing. It's moving farther and farther down vertically. Its speed is increasing. It starts with an initial speed of 0, and by the time it splashes into the water, we can express its speed with this arrow and say, right, it's some large velocity. So even though its position and speed increase, its acceleration does not increase. Right when you first let it go, it's accelerating at 9.8 meters per second. Halfway down, it's accelerating at 9.8 meters per second. When it hits the water, it's still, the instant just before it hits the water, it's accelerating at 9.8 meters per second. This is the same thing as 20 miles per hour per second. So after 1 second, the rock's traveling at 20 miles per hour. After 2 seconds, it's falling at 40 miles per hour. And anytime, it just keeps adding the same speed for every additional second that goes by. But because we like to use metric, 20 miles per hour and 9.8 meters per second are the same thing. So acceleration due to gravity is one of our best examples of uniform acceleration. And uniform acceleration implies that the average value and the instantaneous value are one and the same. And in that case, we can come up with another one of our kinematics equations. So I no longer have to distinguish between the bar or the subscript INST because we know they're both going to mean the same thing. So we just say A. A is equal to delta V over T. But delta V means change in. It means take the final value minus the initial value. That's the change in velocity. So if I multiply both sides of this equation by t, now I have AT, here's step 1, step 2. AT is equal to V minus V naught. So let's add a V naught to both sides of the equation. So we get V naught plus AT is equal to V final. And then if I just transpose the equation, finally we get V equals V naught plus AT. And I hope you recognize this. That's another one of our 4 kinematics equations. So the first one we stated came directly from saying our definition of average speed is delta x over t. So if I cross multiply both sides of that equation, I can get delta x equals v average times t. But because we're dealing in the world of uniform acceleration, v average can be calculated another way. We can say v average is just equal to half of the initial plus the final speeds, and then I still have to multiply by this t. So that's our first kinematics equation. We'll call this kinematics equation number 1, and it just follows from our definition of average velocity. We'll call this kinematics equation number 2, but it just follows from our definition of acceleration. So our first two kinematics equations are really just a way of re-expressing the definition of average velocity and acceleration. Now the other two just come by making some algebraic substitutions. So I want you to notice something about these equations. In the previous video on how we describe motion, on sort of the guts of our study of kinematics, we said there's a few variables we're going to try to relate in the study of kinematics. Kinematics is the study of motion without regard to the cause. So we're not going to mention force or energy or anything like this. We're just going to say, how can we relate change in position, time interval, initial velocity, final velocity, and acceleration? What are the formulas that relate all these quantities? So there are 1, 2, 3, 4, 5 quantities. Now, out of those 5, 4 of them appear in equation number 1. We have delta x, we have t, we have initial velocity, and we have final velocity, but acceleration is missing in that equation. Let's look at equation number 2. We've got final velocity, initial velocity, acceleration, and time, but change in position is missing. Well, here's where I'm going with this. There are a total of 4 kinematics equations. Now, the one thing that we need to know about to study the motion of an object is if that object started at a state of rest, it needs to be given. But if the object is initially in motion when we begin studying its motion, that also needs to be given. So we can never discount initial velocity. If there is an initial velocity, that would always have to be stated. But sometimes we might not know anything about the object's acceleration, but in cases like that, there's still an equation that we can apply to analyze the motion of the object. And likewise, we might not know anything about the distance traveled by an object, but there's still an equation that's useful in cases like that. But notice in both these cases, like I said, initial velocity is given. If there is an initial velocity, it has to appear in the kinematics equation. So there's probably a kinematics equation. Oops. So remember, we always have to have that quantity. So we already know there's an equation that's useful when we're not asked about or given the acceleration of the object. There's a useful kinematics equation when we're not asked about or given the distance traveled. Is there a useful kinematics equation in cases where we're not given the final velocity of an object, right? What if we're given position, time, initial velocity, and acceleration, but we're not asked for and we're not told anything about final velocity? Well, let's say we tried to use equation number 1 for a problem like that. So we tried delta x is equal to 1/2 v naught plus v multiplied by t, but we don't know anything about the final velocity. Well, then we would have to substitute. We can say this equation, number 2, gives us a way of finding the final velocity. So let's make a substitution. We can substitute in place of v naught plus at. After all, that's what final velocity is equal to. So we're going to derive our third kinematics equation by substituting equation number 2 into equation number 1. So this is just basic algebra work here, right? So this becomes 1/2 times v naught plus at, and all of this is multiplied by t. So this means distance traveled. Let's multiply both sides of the equation by 2. So, sorry here, 2 times the distance traveled is equal to, let's see, v naught plus v naught would give me 2v naught. And then we have plus a t. Okay. Oh, and then all of that is multiplied by t. So let's distribute 2 delta x is equal to 2 v naught t plus at squared. Right? I had to distribute the t to both of these terms. And then, well, I changed my mind. I know I multiplied by 2 earlier. Let me divide both sides of the equation by 2. So we get delta x is equal to v naught t plus, well, I'd have to divide this term by 2, which canceled it out, but I also have to divide this term by 2, so plus 1/2 at squared. There it is. You recognize that as a third kinematics equation. So we'll call this one number 3. So you know where I'm going with this one. The last thing would be to say, what if there was a situation where a problem is described telling us about the motion of an object, and although we always have to be given initial velocity, maybe instead of being uncertain about the acceleration, which would lead to the use of equation number 1, or being uncertain about the distance traveled, which would lead to the application of equation number 2, or even being uncertain about the final velocity, which would lead to equation number 3. Notice all the symbols are here except for final velocity v. What would be the last possible case here? So we've already seen the equation that's useful when we don't know acceleration. We've seen the equation useful when we don't know distance, and the useful equation when we don't know final velocity. We always have to be given initial velocity. So what we're looking for is, can we come up with an equation that's useful when time is not given or asked for? So we need to substitute a way for time. So let's do the same thing we did in deriving equation number 3. To derive equation number 4, let's start out by restating equation number 1. Delta x equals 1/2 v naught plus v times t. But this time, instead of substituting for v, let's find a way to substitute for t. Well, we can do that also by going back to our equation that describes the definition of acceleration. Acceleration is equal to change in velocity divided by time. So let me cross multiply. Multiply both sides of the equation by t, and then divide both sides by a. So the t cancels out. Here the a cancels out. We get time is equal to change in velocity divided by acceleration. But change in velocity is final velocity minus initial. So there's a quantity I can substitute in place of t. So we've got step 1. Let's go to step number 2. We get delta x is equal to 1/2 v naught plus v times v minus v naught over a. So let me multiply both sides of this equation by 2a. So the 1/2 and the 2 cancel, the a cancels. So now in step 3 I have 2a delta x is equal to v naught plus v multiplied by v minus v naught. I suppose this can be rewritten right here as v plus v naught. Okay, so FOIL, first, outer, inner, last. So this side of the equation, doesn't it become v squared minus v naught squared? Yeah. Okay, so then step number 4, what if I just add v naught squared to both sides of the equation? I get v naught squared plus 2a delta x is equal to v squared. And then if I transpose the equation, v squared equals v naught squared plus 2a delta x. So now I feel a lot better. Up until this point in the semester, I've been stating these four equations. Delta x equals 1/2 v naught plus v multiplied by t. V equals v naught plus at. Delta x equals v naught t plus 1/2 at squared. V squared equals v initial squared plus 2a delta x. Equations 1, 2, 3, and 4. And up until now, I've just stated them. I just told you. There are kinematics equations. You will memorize them. We will be applying them. And at some point, I'll tell you where they came from. Well, we're past that point now. This equation comes from the definition of average velocity. This equation comes from the definition of acceleration. And then these last two come from making substitutions between those two first equations. And these become our useful kinematics equations. So now I feel like I need to get to the point that I show you that these equations are in some way useful. Well, from the lab that we've already done, you've seen that this equation can be useful if we change our study of motion along a horizontal axis to a study of motion along a vertical axis. Then I can re-express this equation as delta y equals v initial times time plus 1/2 at squared. Now sometimes initial velocity is 0, like when you just release an object from a state of rest. So that equation becomes delta y equals 1/2 at squared. And in a case where gravity causes the acceleration, then we say delta y equals 1/2 gt squared. But you can apply algebra to this equation and rearrange and solve for t. So if we multiply both sides of the equation by 2, and at the same time divide both sides of the equation by g, then we end up with t squared is equal to 2 delta y over g. And if we take the square root of both sides of the equation, t is the square root of 2 delta y over g. Now, how is that useful? You can make a measurement of the distance that a ruler falls through your fingers, and from that, you can indirectly determine your reaction time. So there are a lot of other useful examples of how we might apply all four of these equations, and that's going to be the emphasis for the rest of this unit of study. But for now, take comfort in knowing that these equations do not appear out of thin air. There's a rationale for the four of these kinematics equations.